Okay, I guess we can start this afternoon session. And the first speaker is Pierre Heidmann, who's coming back home in a sense. And we'll talk about non-BPS topological solitons in supergravity.
Okay, so thank you very much for being here. I have the microphone. Yeah. I have one. So first, thank to Nick, Yosif, and also people at the Secretary of SACLE for organizing this conference in person again. And Andrea, okay. So it's very nice. So the subject of the talk today will be about constructing BPS horizonless geometry in supergravity. So it's work in progress and also work done with in collaboration with Ibrahim Abba, Peter Veck, who is here, a student at Johns Hopkins, and also Anindya Day, a postdoc there. So for a long period of time, black holes have been a theoretical laboratory to understand quantum gravity. But recently, I mean, black holes are also physical objects that can be observed and analyzed directly by gravitational wave detection or direct imaging. So this leads to two questions that one can ask, which is, for instance, what is the spectrum of ultra-compact object we can expect beyond general relativity? So there are a lot of models for that, but here we can also wonder what can arise directly from quantum gravity theories, such as string theory and object from supergravity. So from work by Mathur almost 20 years ago, it's expected that the scale where quantum gravity emerge is not really a Planck length from the classical singularity, but at the horizon scale. So we can expect to have quantum gravity objects which are very large and big at the size of the horizon. Moreover, in the supersymmetry, we have constructed through the microstate geometry program a lot of quantum gravity states that are coherent enough to have a description in terms of gravitational solitons, so smooth horizonless geometries in supergravity theories. So a related question to the first one is, can we also expect coherent quantum gravity states as non-supersymmetric objects that can a priori exist in the universe? So the big challenge to construct non-supersymmetric objects is we need to deal with Einstein equations that are a priori very complicated partial differential equations. And moreover, we need to construct objects that are with non-trivial topologies and sources. So we will break a lot of symmetries, and then the equations will be quite hard to solve. So before really discussing any kind of formalism to extract solution, we can ask what could be horizonless smooth geometries, solitons in supergravity. So since Einstein equations are nonlinear theory, one can expect to have solitons there, but there are no-go theorems along the road that make the construction non-trivial. This no-go theorem, the no soliton in 4 dimensions, that has been derived right after general relativity has been written down. So if you take 4-dimensional GR in vacuum, you consider only solutions that are asymptotically flat, topologically trivial and globally stationary, then you have no soliton essentially. The only solution is flat space, so no matter, nothing, and you have no states in 4-dimensional GR. Hopefully you have loopholes that emerge naturally from string theory and supergravity, which is if you add extra compact dimensions to your 4-dimensional spacetime, if you add topology and electromagnetic flux, then you expect to have solutions that are non-trivial and smooth and horizonless. So essentially, how does it work? You can have solutions that are asymptotically flat, for instance, with extra compact dimension, for instance, a tori in n dimension, and a new form of matter will emerge from the degeneracy of those extra dimension in the space-time, and this will form bubbles of space-time supported by flux. So here it's what we can expect from supergravity. But the big question is, can we construct such smooth geometry in the non-supersymmetric regime, make them in a large phase space of solution? and ultimately build solutions that are very close to Schwarzschild or Kerr black holes, and ultimately black hole microstates, Schwarzschild and Kerr black hole microstates. Okay, so for this talk, I will first describe formalism to construct non-supersymmetric solution supergravity. After describing the formalism, I will explicitly construct solutions and then construct solutions that are asymptotically neutral, made of bubbles of spacetimes that are supported by flux. I think I will have no time, but maybe if I have a bit of time, I will discuss the stability of this solution and the phenomenology, which are important questions that we need to address for non-supersymmetric solution. For supersymmetric solution without dynamics, I mean, everything here is stable and nice, but here the question of stability of those non-supersymmetric solution is important. Okay, so let's start by a formalism for non-supersymmetric solution in supergravity. So we take a supergravity theory like type 2b, and we will try to solve Einstein equations. So for that, we need, of course, assumptions to simplify the equation of motion. So the usual trick, which is a trick that has been derived by Weil long ago, which is to consider a two-dimensional problem and consider axially symmetric background, which are also static, so no dt and no cross term along the time. And since we want some, I will consider only a d1, d5 flux. So I will have an internal space which is a T4 and two S1s, where the S1 times T4 will be wrapped by d5 brane, and this S1 is an extra S1 on the three-dimensional base. So the axial symmetry induces that we can have an ansatz of trick where I have a three-dimensional base that I can write down in cylindrical coordinate. Essentially, rho and z are so how do you call that? The cylindrical radial distance rho, and z is the axis of symmetry of my solution, and phi is the angle of symmetry. I have, as I said, two S1s that I will parameterize here by y1 and y2, with several warp factor all along here. I have an extra T4 parameterized by this x coordinate, and of course a time direction. So I want geometries with a non-trivial flux background. So I will take here, for simplicity, two type of flux, a D1 flux. I have an electric gauge potential here, T, and a magnetic one, H. Also, for simplicity, I will assume certain self-duality condition on this flux, which essentially means that the D1 and D5 charges will be equal. So this is a simple playground, essentially, where I have a certain number of warp factor and gauge potential H and T that are depending only on rho and z, which are the coordinate in my base. Okay, so the nice thing about that is that even if non-trivial force, matter field, the Einstein equation decoupled in different sectors that are a priori integrable. Essentially, I have first one sector which concern this warp factor z, which coupled to the gauge potential. I will explain what are those nonlinear coupled equations just later. And I have vacuum Weil sectors which concern the warp factor W's. Those ones are very simple equation. Essentially, the log of W's are harmonic function, where here the delta is the Laplace in flat space. And finally, I have one last warp factor here, new in the base, that gives the nature of the base, where it's a non-trivial equations, but it's a simple equation to integrate, where everything here can be considered as a source for this warp factor nu. So a priori, if we know a way to solve those non-trivial coupled equation there, we have a very simple roadmap. We can solve here its harmonic functions, and then back there we can just integrate. So we can solve.
Yeah, why do you think this warp factor? Like, what's the reason?
I mean, it's just. I mean, it's here because it's. I mean, you start with a specific ansatz here, axially symmetric. So you expect to have such a warp factor dependence here. I mean, if you freeze it, you will have degrees of freedom, essentially. Yeah. Yeah. I mean, you don't expect the base to be flat if you non-supersymmetric.
Oh, right.
Okay, so let's have a look to this Maxwell sector. So it's non-trivial differential equation, but the nice remark is that they can be mapped to vacuum Einstein equation for four-dimensional stationary axially symmetric spacetime. So essentially, if I consider just a 4D Einstein vacuum and an ansatz of metric as follows, where Z and H are the same as the previous one, the equation I will obtain are exactly the same as the equation I will type to be. Essentially, the Laplacian of log of Z is induced by this gauge potential that way, and the Maxwell equation gives you something like this, and I can obtain T by just self-duality of the gauge potentials. So why is it an important?
What's X is the sum of the Z and rho and Z?
Yeah, it's rho and Z. Yeah, yeah.
It's implicitly summed.
Yeah, exactly. So it's still very hard to solve because, I mean, we don't really know how to solve this equation. The nice thing is, I mean, four-dimensional GR have been studied a lot, obviously. And so we can use the knowledge in those fields to hear a very different kind of objective, a goal, which is to build a supergravity solution. Essentially, for those equations, there are a lot of solutions, which are, for instance, the Majumdar-Papapetrou solution. You have also the multi-Kerr solution, the multi-Rison-Nordstrom, etc. on the line. You have a lot of solutions of those equations that we can just use. We also know very well the integrable structure of those equations, which is related to the Geiger group. And there is also many methods to generate new solutions from those equations by inverse scattering or N's potential method. So essentially, we can use these technologies that has been made for constructing bound states of black hole in 4D, here in the context of building non-supersymmetric solitons in gravity, in supergravity. Okay, so we can also take a broader perspective, the most general ansatz that leads to linear to those kind of equation. And for instance, take an ansatz where you have no, like, just not only D1 and D5 flux, but D1, D5P, and KKM flux, and you will have the same kind of equations at the very end. So here you have like a different kind of Z, which Z1 is related to the D1 flux. T1 is electric potential for the D1 branes. You have ZP for the P, Z5 for the D5, and Z0 for the KKM. You have also those Ws here, which are also vacuum arbitrary harmonic functions. And also those Ws are deformation of the T4. So here you have the same kind of properties in a sense that everything decoupled in sectors. You have 4 sectors for each kind of flux with their associated warp factor, and 4 vacuum Weil sectors, and at the very end you can solve for the base sector. So this is the most general ansatz where everything decouples nicely, and you can hope solving the equation and building non-supersymmetric solitons. I mean, you can dualize. I mean, you can weak rotate Y2 and T, but it doesn't give you something.
I mean, there's no DT plus space-time direction.
Not really, but you can still weak rotate Y2 with T. You can still, if you weak rotate the, I mean, you can put H0 into the time direction. I mean, if you weak rotate Y2 and T, for instance, but I didn't find any. Yeah.
I just think just along the lines of simple Kerr. I mean, you can't do some generalization of Kerr on this.
I mean, here, for instance, you can take the Euclidean Kerr. It's a solution of this frame, and then go back to the time. I mean, you can consider here like T, and you can put a minus there, and I will still have an H0 there, and you can put Y2 there and a plus. It's still the same equation. So the previous playground is just a subclass of this very general ansatz where you have equal D1 and D5 charge and no momentum and KKM charge. So now we have a kind of roadmap to construct solution. In a sense, we started with supergravity framework where a priori it's hard to solve Einstein equations, but we have seen that we decouple in sectors where the integrable structure is well established, and we can hope building solutions. So before building solution, let's discuss a bit what kind of boundary condition we can impose to the solution. For the asymptotic first, if you take at very large distance, let's assume that those W's and the nu goes to 1. If, for instance, we succeed to impose all the Z to go to 1, you can see that all the metric component goes to 1, and you will recover a Minkowski in 4 dimensions times some compact circle, so you will be asymptotically flat. By playing a bit with this Z0 here and making, for instance, 1 over R, where R is square root of rho square plus Z square, you can make it asymptotically flat in 5 dimensions. It's a bit like the supersymmetric solutions. But also you can have more exotic boundary by, if you succeed to make those Z, all the Z to go to 1 over R, you will build asymptotically ADS2 solution, and you can also make ADS3 solutions. So this is what you can hope as a boundary condition, asymptotic boundary conditions. So now let's discuss what you can source. So in the interior of your geometry, how you can source those kind of solutions. So by axial symmetry, you have essentially 2 types of source. You have first source and rod source, which are extended segment source. So for the point source, there are a few issues in the sense that because the log of W are harmonic functions, it will mean that at the source, the W's will behave like exponential of 1R, which is very divergent, very singular. And usually you cannot source them, so you need to take them trivial. And at the very end, the Z will be exactly like the BPS ansatz, and you will recover the BPS D1, D5P, KKM ansatz. And so by putting point source, you will recover the BPS regime. However, on the other side, by having a rod segment, here you can non-trivially solve the thing, and as the source will be naturally non-supersymmetric, they will induce mass and charge. And here you can expect to have something which is non-supersymmetric. So here you will be by sourcing internally with rods on the Z-axis, you can be non-supersymmetric, and the question is, can you have non-supersymmetric bubbling geometries? So we'll consider source. What type of rod source will lead to a regular? Yeah.
What is the near the rod? How does the mechanism?
Here I will explain a bit what you can expect, like what are the physical regular rod source you can have. But okay, usually they will make some extra dimensions to degenerate smoothly. Like,
right, so it's going to be like orbifold rods.
Yeah, it will be a bolt essentially. Okay. So I will just explain how you can get. Okay. So yeah, we can have a rod source. What are the rods that will lead to something which is a regular source? So here I usually describe the geometry in the papers with those kind of weird representation. Essentially, here I represent what you have as a source. Here is the behavior of each of the extra dimension. For instance, the phi circle, the y2 circle, the y1 circle on the z-axis. So if, for instance, if I don't have any source, the phi circle here shrink on the z-axis. So I have essentially a 0 size phi circle everywhere on the z-axis, while all the other guys have a finite and finite size. But if I succeed to, on a segment, on a rod, if I succeed, for instance, to make all the z here, while all the w's and everything else is finite, all the z goes to infinity, you can check that here this guy will shrink, like the time fiber will shrink, while all the other guy will have a finite size. So essentially, the local metric here at the rods will be some kind of d rho square minus rho square dt square, which is the metric at the horizon of a static black hole. So because all the z will be turned on exactly here, you will have a 4-charge non-supersymmetric black hole, like the Stepchich and Hume black hole. And essentially what it will induce, it will make the phi circle to blow up. As you can see here, you have z1, z5, z0, rho square, which will have a finite value. But you can make something more funny. For instance, you can induce a degeneracy of the y2 circle. Let's take z0 to go to infinity, e to nu to go to 0. You will have similar kind of metric, but now you will have d rho square plus rho square dy2 square. So the y2 circle will degenerate and replace essentially the phi circle. So the phi circle will have a big finite side there, and the y2 circle will shrink on the z-axis. Because only z0 is turned on, it will be a bolt, the KKM flux wrapping the geometry. Equally, you can do the same for the y1 circle there. you can force it by making also some choice of degeneracy at the rod, and you will induce a bolt where the Y1 circle shrink. Something more exotic, because you cannot do that with supersymmetric solution, you can make some T4 direction to shrink to 0 size at some segment also by just also choosing different kind of internal boundary condition. So those are the essentially 8, or I don't know, maybe 1, 2, 3, 4. I think it's 8 type of source you can have for this kind of framework, either black holes, either regular bubble locus. The main problem is usually with those kind of Einstein solution, because they are non-supersymmetric objects with more mass than charge, they will attract each other and they want to collapse. So they need a mechanism to support from this collapse, and we'll have a string with negative tension, which is essentially like a spring pushing the object far from each other, which physically means a conical excess on the z-axis. Essentially, you have the phi circles that shrink in between the guy, where you have coefficient S here, which is bigger than 1, which means that the local space-time has more than 2 pi periodicity. And those are objects that are string with negative tension. So it's a singularity that we cannot resolve in supergravity. So we want to avoid such a kind of geometry. Hopefully, it has been observed almost 20 years ago with vacuum solutions that by gluing sources together like this, I took the exact same sources as before, I glue them on a line. The phi circle didn't shrink anymore between each object, and the stress disappear. So here you have a geometry which is perfectly without conical excess. You still have black holes, but to get rid of black holes, you just have to take no black hole source, and you have a chain of balls on a line, which are inherently non-supersymmetric, free from any curvature singularity, and of horizon is just a chain of non-supersymmetric bubbles supported by D1, D5P, KKM flux. So here is the idea. In the sense that we have the equation of motion, we know what type of internal boundary condition and asymptotics we need to impose. The question is now how to really derive how the back reaction of the source on the system of equations, essentially. So derive all the Z, W, etc. Sourced by this type of rods. Okay, so in the first series of projects, we found a linear branch to solve those equations. So this is the one that we have. We find that the non-trivial nonlinear equations for Z and each gauge potential can be solved by linear equations. Essentially, you can extract from each of those sectors an arbitrary harmonic function. So I can take, for instance, an harmonic function L, and the Z will be expressed as a sinh of L with 2 parameters A and B that are real. And the gauge potential are also easily obtained from this harmonic function L.
For you, harmonic means in 2-dimensional, rho and Z.
Yeah, exactly. Yeah, everything is actually symmetric here. But yeah, so we start with something which is not linear, and here you just reduce to something which is linear, and we know how to solve. The vacuum valve sector, so all the W's, they are directly harmonic, the log are harmonic, so we know how to solve also. And the remaining things to solve is the nu there, which is the last warp factor to solve, and it's a simple equation to integrate, so we know how to do that. So at the very end, this linear branch is very nice in the sense that everything is given in terms of 8 harmonic functions, and we just have to put the source we want, the rods, etc., and solve it and obtain solution. So this was we extract solution from this linear branch in this paper there. So let's discuss a bit the regime of parameter we can have. So as I told you, I mean, we have 8 harmonic functions. We have also a series of a number of constant A and B that we can freely tune here. So let's see what happens if I take A and B to 0, for instance. So you can see here that taking A to 0 make the electric gauge potential to be the inverse of the gravitational potential. So this is something which is very BPS-like. And also you can see that taking A and B to 0 here make the Z proportional to L. So Z will be harmonic itself. And so you can check that by taking those parameters to 0, you will be in the BPS regime for those Z and T. On the other side, by taking A and B to infinity and rescaling L appropriately, you will make the T here essentially to be a constant. So you kill the gauge potential. So you're in the vacuum regime where everything is vacuum and the flux are 0 everywhere. And in between, you are freely non-BPS. So these A and B parameters are free parameters that you can use to tune from the BPS regime to arbitrary far in the non-supersymmetric regime. So it's very unexpected that we can derive a linear ansatz that can be arbitrarily non-BPS, but it's what we have there. Okay, so at the very end, we have 8 harmonic function. We can solve it by rod, impose the internal boundary condition and the asymptotic we also want, and construct the solution I described before. So it's essentially the first large class of non-supersymmetric bubbling solution by making this chain of rods. I'll just describe a bit the pros and cons of this solution. I will not really give the metric, etc., because it's slightly complicated, but I will just describe the pros and cons. So the pros, what is very nice, it's only BPS linear ansatz. So usually it's expected that if you want to construct non-trivial topological structure in the non-supersymmetric regime, you will need to use the full nonlinearity of Einstein equations. But here we have shown that we can have source which is arbitrarily far from each other and sort it linearly, and you are arbitrary non-BPS. So this is kind of a nice remark, and it means also easy to manipulate. At the very end, we build a lot of solutions that are just made of bubble on a line, and we call it a bubble bag-end geometries. Why? Just because they look, I mean, the geometry look like a bag of bubbles, which is a chain of bubbles. So we studied a bit the geometry of that guy. You have essentially a wrapping, it's a strong shift, and the space-time open up in a very big bag of bubbles. So that's we call it bubble bag-end. Moreover, I mean, we have observed that the near BPS solutions, and so as you approach by taking this A and B parameter close to 0, are very close to supersymmetric black holes. So essentially, we resolve a supersymmetric horizon by just moving slightly from the BPS regime. So it's indirectly means that you can be, I mean, those geometry are ultra compact. I mean, they can be, they can have a very long throat. At least the near BPS one are very close to the black hole geometries. So it doesn't mean that it's microstates of BPS black holes, but it means at least that you can have very compact geometries. Also, I mean, as I said, you can tune the asymptotics. So you can also build asymptotic to solutions that are asymptotic to ADS3 and ADS2. So it will be the first large phase space of bubbling solution that are asymptotic to ADS and non-supersymmetric.
Sorry, ADS4 you can.
I didn't manage, but maybe it's possible. I don't know.
Can you make this solution supersymmetric, but not?
How can you do?
Like there are certain black holes in 5 dimensions that you can make symmetric, but not extreme. Like extremality is supersymmetric.
Okay.
So can you make this?
No, the other way around. The other way.
Yeah, I think it's the other one.
Supersymmetric means pH equals 0.
Yeah.
Yeah, that's what I mean. Yeah, like BPS, but like supersymmetric only, but not supersymmetric and extreme.
No, it's here, like extremal, but non-supersymmetric.
Yes.
I don't know. I mean, non-supersymmetric, supersymmetric and extremal. What?
5-dimensional black hole, which in Euclidean you can parameter by 4 parameters, you can set one of them to be something, and that black hole would be supersymmetric, but we would not have like like the Euclidean.
Okay. Yeah, it might be possible. I mean, if you can have some non-rotating solution, it might be possible. I mean, if the black hole can be non-rotating and still there, I think it's doable. I don't know. I mean,
supposed to converge or diverge.
yeah. I mean, my expectation.
The overall
volume always becomes large. So the point is, by holography, the transverse volume never decreases. So what's happening for him, the space-time volume increases, but the torus shrinks.
Yeah.
So if you look at the full 10D volume, the full 10D volume always goes down. The 4D volume does that, but the price to pay is that the tori become larger. So this is confusing because this appears to contradict the holographic dictionary. Because
Yeah.
the holographic surfaces, and the more you go out, the area should increase. Yeah. But the point is, it's really cheating that,
I mean, I don't know for geometrics, I don't, because it's really like here, it's really the S2. I mean, those geometries are, for instance, asymptotically Minkowski R1,3. So you have a natural S2 that decrease. Yeah, essentially, I have but the geodesic still, I think, would see this minimal surface here. The minimal S2 surface. But it's indeed, you have some tori around that make everything to be getting small. Yeah.
Otherwise, I was screaming at them when they had a paper 2 years ago. But
Yeah.
Yeah, no, it's really.
But I would like to do the geodesic because I still think that you should see this minimal S2 because it's where the geodesic live. Yeah. Yeah, no, yeah. So the cons of those this linear ansatz is that they are complicated. I mean, they have regularity conditions, obviously, to have this kind of chain of bubbles like the BPS solution, and they are very complicated here. So usually I have to use numerics or some assumptions that are not super nice to use. So this is kind of a cons. Also, they are quite rigid solution in a sense that you have no real moduli to tune. Essentially, it's not like the BPS case where you have a family of solution where everything can scale very closely towards the supersymmetric black hole. Here, it's not there, essentially because we have started with an ansatz that are not enough to have this kind of scaling topology. And at the very end, which is quite annoying to have neutral solution in the sense that each bubble on the line here, they are supported by flux, obviously, but the mass over charge ratio is constant for all of them, given by those parameter A and B I described before. So essentially, we cannot have solution with like a bubble with charge Q and a bubble with charge minus Q, and at the very end have something neutral. So, I mean, all the objects we have built here are mostly in the regime of Rice-Nordstrom or Svedicenium, where the charge is non-zero. Actually, there are still algebraic equations, like polynomial equations, but they can be all complex. Yeah, I don't know. Yeah, there may be for everything we did, indeed, we found at least one solution, but it's not obvious that there are one. Yeah. Yeah. Yeah.
You should have moduli to move them off center, but you cannot do that. His ansatz is always with the points on the center, so then he doesn't have any moduli. When the points are on the center, the number of bubble equations and the number of positions is the same. So then. But there should be. There should be. There should be is by construction because it's a non-extremal microstate, so it should be unstable.
I mean, I will have time to discuss stability, but.
No, I'm just curious as to whether these solutions are stable or not.
I mean, we've studied a bit of stability. I mean, the classically stable, thermodynamically stable, but after, like in the full string theory background, we don't know.
Did you check stability
to non-axisymmetric perturbations?
I mean, we check for the one bubble guy, like the ingredients. Like here, we're doing chain of bubbles, but for the one bubble guy, it's
folding and things like that. Folding up into, if you've got two bubbles, one folds the other and that.
The thing is, if you touch two bubbles, it forms one big one. I mean, the topology changes very non-trivially. So it's not like you take one bubble, you glue them, and it makes like two. It's like the topology is very different. By gluing them together, you drastically change the topology. But like just for the ingredient we're putting on the line here, if you just take one, it's classically stable and thermodynamically metastable. I mean, I don't know if I'm not sure I will have time with the questions, but we'll see. Yeah. Okay, so we have this ansatz where we have built non-supersymmetric solitons in supergravity. Now we would like to build something which is more like in the real world, so something Schwarzschild-like. So we still don't have any rotation, no spin, but something which is neutral. So to do that, we need to get rid of the linear ansatz. So I will go back for simplicity to this very complicated thing with the 4 gauge fields, etc., to the playground where I have essentially d1, d5 equal d1, d5 charge. So how to proceed essentially? I mean, we have this equation for the warp factor Z and the gauge potential. And the only thing we need is to extract something where we can play a bit with the charge compared to the mass. Oh yeah, I mean you can do both. It's just change the sign. Whatever. Yeah, for me, I think here it's Euclidean. It just changed psi and it's sorry. It just change the sign. It doesn't change mass. I mean, it doesn't change the equation. You can go from Euclidean. I mean, it's just a rotation. So it was just like if you do h goes to IH, it will be the same as. So it will just bring a minus somewhere.
Sure, it changes the entire nature of the solution, though.
Yeah, the physics, of course, is different, but the equations are the same and the solution are. Okay. Sorry?
There's no conical singularity.
For what? No, the goal is to impose to have no. I mean, like by imposing not having any conical singularity will like fix the length, but you have to do that. That's why you have those equations that constrain the geometry. Yeah. So what we can do is just go to the literature. I mean, people have worked solution in GR in this background, and for instance, consider a very non-trivial solutions that are built physically like a chain of charged black holes on a line. Been derived in '94 by those guys, and use this ansatz for building bubbling solution where we can play with the charge here. So essentially, I mean, we don't have to take the n soliton solution. We can start with just 2 rods where you have a mass and a charge parameter. This will give us from those solutions Z and H and T. And for us, we will decorate this kind of equation with the W1 and W2 to make something which will not correspond to a chain of black holes, but a chain of rods where Y1 and Y2 essentially shrink. But at the very end, we want to make a chain of balls where the charge are opposite, like you have minus Q and plus Q, build something which is neutral. So it's what we have done. We took this solution from this 4D solution and make something in type 2B, which is a chain of balls which is neutral. Essentially, you have a chain of 3 bubbles. One here as a D1, D5 charge minus Q, and one here as a D1, D5 charge Q, and induce a mass which is larger than this. And we made, to have something without any strut in between, we made a vacuum bubble there where the 2 circles shrink. So at the very end, we have something which is neutral, made of 2 non-supersymmetric D1, D5 bubbles on a vacuum bubble. So you can consider this as a kind of non-BPS D1, D5 bubble dipole. Because it's still neutral, you have an electromagnetic dipole moment. So then you can study the phase space. I mean, you have regularity condition as like this, the questions. I mean, you want to avoid any conical singularity or just conical excess. So you have everything given in terms of the full mass of the background. Ry1 is the size of the extra dimension, so the periodicity of those angles, and K1 and K is potential bifold parameter at the bubbles. Then you have many corners of the phase space. We observe that you can build geometries that are very large and compact in size, or with very large and electromagnetic dipole, or also very large and internal charges. But still, we wanted to focus on geometries that will look very much like Schwarzschild. We found that for this, we need to assume that take the geometries that are where the mass of the objects are way larger than the extra dimensional radius, and where one of the orbifold parameter is super large and essentially larger than the ratio between the mass and the extra dimension parameter. The other one is over the one. In this case, I mean, the charge, the D1, D5 charge of the bubbles on top and, of the vacuum bubbles are quite, I mean, are small in a sense that, that it's not perfectly m squared, but it's scaled down extra dimensional radius.
Big.
I mean, in the sense that you can do whatever you want, but here in this corner, it's where it's very like deep, large redshift, very Schwarzschild.
Okay, so if you don't take K very big,
You can have a very big
fat thing,
fat
but very
with a-
shallow.
Yeah, with like a huge electromagnetic dipole. And
But it's shallow. It doesn't
yeah,
have a big
yeah, the
redshift.
redshift. I will describe the redshift right after. I mean,
But no. The Schwarzschild black hole has high redshift. So depth. Okay, let's for term for microscopic geometries. Depth when you're not BPS means redshift from the bubbles to the infinity, and so shallow.
Yeah,
sounds like K is.
I will describe the redshift. Right.
And there's also the obvious question about instability, why the minus Q doesn't slide around the vacuum bubble to another.
Yeah, the thing is here. I mean, I describe it that way, but it's not how it is. I mean, yeah. I just make the two bubbles very obvious, but it's. I mean, if you approach the guy, it doesn't look like this Mickey thing.
No, I know it's picture, but is there what's the motion? Is there a moduli space on that principle? In practice, you can't do it because it's going to break axisymmetry. But in principle, isn't there a moduli space where it could fold over and the plus Q could then annihilate against the minus Q?
I don't know. Yeah, it's hard to say. I can.
It's not necessarily.
It's just it's not two objects that you cannot easily make a. So it can be very. It can just spread. I don't know. Okay. So what we observed in this regime is that the two bubbles here, the D1, D5 bubbles, are very close to the BPS limit. Once again, they are very close to they are very near BPS, and we essentially observed that in the BPS limit. So if you make, they approach a bound state not of bubbles, so they are essentially very small size, but a bound state of BPS black holes, which are the well-known D1, D5 black holes. Essentially, if you take a certain limit of these geometries, you can see that they will scale towards so a D1, D5 bar anti-BPS black hole here, and a D1, D5 BPS black hole there. So it's also, these geometries are also very interesting in the sense that it's a bound state of two BPS and anti-BPS black holes on a vacuum bubble, where the thing is fully neutral and regular.
And the bubbling, so the fact that, so the way to think about the bubbling solution then is that you have the singular configuration which has a D1, D5 and then D1, D5, and then you have a back reaction of the singular configuration which blows up the bubble.
Yeah, essentially, yeah. But I'm sure you can also resolve this guy by doing so, and not this thing.
Just to clarify, the vacuum bubble, you mean the sort of Witten sort of vacuum?
Yeah, it's a bubble of nothing.
So the bubble of nothing is actually normally would expand to space time, but the attraction of the black holes is actually stabilizing the bubble of nothing.
Yeah, exactly.
Beautiful. Okay, lovely.
So yeah, just this solution are also interesting on their own in a sense that it's two charged BPS D1, D5 black holes that we know, or in a sense that are microscopic black holes. They have near ADS3 times S3 near horizon region, and also their BPS microstates are known as supertubes. And you can also perfectly not resolve the solution, not as I did by moving slightly near BPS, but you can also put a supertube there and anti-supertube there, and also have a smooth geometry with minus Q plus Q and fully neutral. So I think it's the first neutral black hole bound state, which is regular in a sense that they don't made of BPS and anti-BPS partner, where they don't collapse due to these vacuum bubbles that provide this necessary repulsion to make them, well separated. So our bubbling solution is essentially resolve the horizon of these BPS guys by moving from in the non-BPS regime. And at the very end here, we also had the same regime as Schwarzschild by doing black hole bound states, supersymmetric black hole bound states. Excuse me? It's very, like the vacuum bubble in the middle is a very unstable object. Here, the topology we're using here to support those two, you're saying why is it stable or unstable?
From annihilating.
I'm not sure.
What keeps the D5 and the D5 bar from annihilating each other?
I mean, here it's static because you have a vacuum bubble in between them. That essentially, I mean, if you like this vacuum bubble, I mean, it's actually a computation by Heidmann and Horowitz. It's a paper there where they study that the vacuum bubble wants to expand
Mhm.
essentially, and you can really compute the acceleration of the vacuum bubble, which will perfectly counterbalance the attraction of the two black holes on the line. I mean, the lack of
but it sounds like you've arranged that by putting the D5 and the D5 bar at opposite poles of the bubble.
Yeah.
But I would think that there would be an instability where they just want to go
Yeah,
towards
this is
the
perfectly
equator and
possible.
annihilate each other.
This is perfectly possible that it's a top of the hill kind of solution.
Okay.
It's also put another way, the vacuum bubble wants to expand. It's trying to expand very symmetrically, but
Right.
expand asymmetrically and blow out the sides. And this won't get all like this. But it's opposite.
Yeah, it's I mean, for this, you need to study the full perturbation, and this is quite hard. I don't know how it. I mean, I think the intuition that it's expand like this and the two black holes. I mean, I think it's not the right one in the sense that here it's just a picture. So it's the topology is very different. Like the topology here, it's not a pure vacuum bubble. It's not an S2. I mean, the vacuum bubble is an S2 there. While here it's not that, because at the pole you have two at the S3 point. So it's very different. So it's unclear. I mean, the perturbation of the background is really unclear.
But the fact that you get a solution which has actually not trivial.
The microphone, please.
Yeah.
I hope they see that on the camera. We should have a camera for it.
But the fact that you have a solution which has an honest to goodness brain and anti-brain charge and it's fully supersymmetric, that's actually quite relevant also for the work on anti-brains and Klebanov-Strassler and so on, because there we had big arguments that anti-brains, when you put them in Klebanov-Strassler, they tend to give you a non-supersymmetric, they tend to give you some singularity and so on and so forth. So in a sense, your work is establishing that you put some anti-brains in the system, so and then they seem to be happy. At least they give you a good solution. They don't.
Yeah, but for you don't have those. I mean, here you still have a vacuum bubble that brings.
Yeah, but just the fact that you have the back reaction of anti-brains, it doesn't have.
Okay. Yeah.
It doesn't seem to have a horrible effect.
Okay. Okay. So
comment. I mean, the mechanism is really interesting. This particular one may not be stable at all, but if you put enough of them together down the bottom of a long throat, they might be unstable in exactly the right way to make Hawking radiation. So instability is your friend eventually.
Yeah, maybe. It depends. Yeah, which type.
Can you put just the 5 rays alone and those ones?
Yeah, you can. Yeah. Yeah, I can do that. And you can also replace the vacuum bubble by something with flux, and it will be not neutral.
And can you put just D5 and D5 and those ones alone?
Yeah, you can.
So just D5, anti-D5, and the bubble in between them, and that's it.
Yeah.
Just
D5 will be very singular, no?
Yeah, sure. But I can tenderize to a D3, and then it will not be singular. Then it will be like a D3 anti-D3 with some topology.
Okay. Yeah, you can do that.
That's okay.
Okay, so now we want to compare to Schwarzschild. I mean, we have those kind of bound state of black holes of supersymmetric and anti-supersymmetric, and we have those bubbling geometries that are neutral. And we want to compare to Schwarzschild geometries. So for that, the first thing we can do is indeed computing the redshift. So the redshift is just the norm of the time-like killing vector in type 2b. So for Schwarzschild, if you embed Schwarzschild in type 2b, it will be just this kind of 1 minus 2 mr over r minus 1. So it's something which is essentially growing very fast, and at the horizon, it's infinity. So we have done that. We have computing the redshift factor, for instance, for the black hole bound state. So essentially what we found is, like, as you approach, the geometry is getting very large and very large. As you approach the vacuum bubble, it's always finite there of order the mass over the height of the dimension, something very large. And at the pole of the vacuum bubble, I mean, you have something where it's infinity, essentially. It's an IDF3 throat. So it's infinity. So you have this kind of teeth on the redshift. Obviously, for the bubbling geometries, everything is smooth, so the redshift should be finite. And what you find is essentially, I mean, these geometries are very close to those geometries in a sense that is very large at the teeth, but it's resolving it with a coefficient, whatever. And you have still some kind of redshift, which is of order m over the extra-dimension side. You cannot really scale it in a sense that you can assume that the mass of the object and the extra-dimensional radius are something given by the boundary. So you don't have scaling parameters, but it's still something, it's a primitive solution where you can have a very large redshift like Schwarzschild. Okay, so this is for the redshift. Now let's discuss a bit the multiple moments. So for Schwarzschild, multiple moments. Here we can wonder what kind of multiple moments we have with those bubbling geometry, and is black holes a bound state. So for that, what we can do is to assume that the external dimensional radius goes to 0. If you do everything simplified, you obtain a singular vacuum solution, and given by this metric where you have only one coefficient m. Essentially, our solution are just resolving these very singular geometries by just considering that those guys are those coefficients are very small. So in different way, either from the bound state of black holes or the with bubbling geometries. But here it's very convenient because computing multiple moments of such geometry is at least slightly easier by compared to deriving it for the full geometry there. Yeah. Yeah, you can see here that the S2 is blowing up. I mean, it's very bad. But everything is resolved as soon as you consider the. Okay, so you can derive the multiple moments. What we found is like Schwarzschild. I mean, the odd multiple moments are 0, but you have very big and huge multiple moments, even ones, in a sense that they scale like m⁻²n + 1, where here Cn is just a coefficient, which I mean, I didn't succeed to find the series, the exact series, but it's something which is always kind of on the 1. You have something which is very big multiple moments. So you have.
So just to clarify, those numbers are really the sort of multiple moments, the bubble of nothing. They don't really contain the information about the D1, D5s. Yeah.
Actually,
no, okay, they do.
I thought. Yeah, no, they do. I mean,
I thought it was just, you know, the big thing here is the bubble of nothing.
No, actually, no. I mean, I mean, here it's the big thing is not the bubble of nothing, because if a bubble of nothing will have no GTT component. Oh. So if you have just a bubble of nothing, there is no redshift.
Yeah, okay.
It's something we discussed at the time. I mean, if you have no bubble of nothing, here it's 1 essentially, and you have some warp factor. I mean, you have some.
I thought you had this sort of hole and the deep throat or this throat, and then at the bottom is a bubble of nothing, and 2 point-like sort of things that are holding the bubble of nothing frozen in place.
Yeah.
So I would have thought that there's a static bubble of nothing, and I thought that would be more reflective of the bubble of nothing.
No, here everything contributes.
Okay. Okay.
Okay, so here it differs a lot from Schwarzschild in the sense that you have large multiple moments. Now, I mean, it's something also I like to compute. Yeah.
Whoa. Can you clarify if I think about it as a replacement of Schwarzschild? So I have an object that has this metric. Where is the horizon?
I mean, here essentially this metric is very singular at r equal to 4 m/3.
Okay.
And essentially our solution there.
So the infinite redshift at r equal 4/3 m.
Yeah, essentially yes, and also like you have, I mean, it's even worse than that. I mean, even if indeed you have a kind of horizon in the sense that this shrink, you have also like this phi circle which is blowing up. So it's highly singular.
This probably is ruled out by gravitational wave experiments already.
I mean, it's also resolved by those. I mean, the geometry I'm considering here, if you approach r equal to 4 m/3, at one point you will completely resolve.
Yes, but away from that point,
is very close to
this is the metric, right?
Yeah. Of all, I mean, you have correction of order those coefficients.
So what I'm asking is whether this is already ruled out by gravitational wave experiments.
I don't know. I mean, it's possible. I mean, yeah.
Approximation away from r equals 4/3 m.
Yeah, yeah, but
okay, so this is what I wanted to hear. Thank you. I understand that, but I just wanted to.
But also, I mean, I think it's very hard. I mean, the gravitational mode here, you need to know the full metric. I mean, like to really compute the quasi-normal mode. Okay, okay.
No, but how do you know it's ruled out? I'd say that it's not. I mean, you need to compute the orbit around. You need to compute the gravity wave signature. I mean, you know, it's not clear that it's ruled out. I mean, you know, once you look at the it is a freaky thing, but if you go around the equator. Yes, but the point is, the question is you have to ask about the merger. So in a merger, where is the second black hole moving? So let's suppose you take a small black hole in this background, you have it follow the.
Okay.
Because nobody's arguing about the fact this is interesting. It's just this example.
No, but this is like 100 times better than boson stars.
Oh, yes.
Okay.
Okay. Sorry. I'm the chairman. I have the right to say that Pierre should answer questions, not the audience.
No, but also, like about the gravitational wave. Here you cannot derive quasi-normal modes in this background.
Quasi-normal. You just have these two objects turning around.
I see. Yeah, just
different properties than Pierre black hole to 4'th black hole.
Yeah, but here you need to go to how do they call, like PN order. I'm sure it's very close to Schwarzschild. No, but in 4 dimension, if you go to 4 dimension, it will look very close. Like you will have those this guy. If you compactify on this guy, you will have extra guys there, and in 4 dimension, it's super close to Schwarzschild.
This is what I was asking you. What is if I want to?
No, but if you do like the binaries guy.
If I want to compare it to 4-dimensional Schwarzschild, what would the metric?
You have to compactify along Y1, Y2. Yeah. So you essentially get an extra square root. You will get this guy power exactly. You need to get asymptotically 1 minus 2m over r.
3/2.
Yeah, 3/2. 3/2. Yeah.
I guess 3/2.
Yeah. You will get this guy in power 3/2.
That's right.
The GTT component in 4 dimension will be this coefficient power 3/2, which is, at least for the first order, it's the same. So you will have, like, for binaries, like it will be very close, like the first linear order will be very close for binaries. But then indeed, when you get closer and closer.
It's just got a photon ring in a very different place though.
Yeah, this is possible. But yeah, it's hard to know. But
anyway,
okay.
But the thing is, those geometries are also like the one we built here are very primitive. You can decorate with more, you can make more bubbles, you can do a lot of things. Here, just to have the first example, but you can do more, and it can maybe scale towards Schwarzschild, even more Schwarzschild. Okay, so just to continue about the properties of the solutions, we can discuss the size of the S2. So the solution are asymptotic to flat Minkowski in 4 dimensions. So we can discuss what is the size of the S2 and think about the size of the S2. Like if you are an falling observer, the size that you will see as you fall down. So usually when you start from infinity, everything goes like the area of the S2 here, which I'm plotting there, goes R squared. So essentially the sphere is increasing, which what we recover here in our geometries. But what happened with our geometries which is also a kind of bag geometry in a sense that the S2 very close to where the source R is blowing up. So essentially you can imagine it as like a bag. You approach as an infalling observer, you reach a minimal S2 there, quite far from the surface of the bubbles. And at one point it opened up in a very big space. So it's blowing up for the bound state of bubbles because bound state of black holes, because you have black hole throat. So like the S2 is infinite, the area of the S2 is infinite there. But for the bound state of bubbles, of course, everything is smooth. So it just ends up at the finite value. So you have just a big space and you end up at a finite point where it's bubbles, plane of bubble. So you have a bad geometry in a sense that it opens up and after reaching a minimal value, which is given here quite far from the source. What we found is the radius of the S2, so the square root of the area essentially, is 1.5 the Schwarzschild radius. So it's kind of compact, not as compact. It's still very unclear what you will see because here we just compute the area of the radius of the S2 and you don't really know what the geodesic.
The photon sphere.
Yeah, exactly.
Yeah, I don't know why. I don't know if you add more degrees of freedom, you can scale more, I don't know. And it's also very obscure. It's possible that this square root, it's not really, you need to know, to do the full geodesics computation, really talk about what you observe when you fall down. Here, I'm just taking the metric and compute the S2. Okay, so I think I will conclude there. But so what we have done is we build an example of a neutral solution in type 2b. made of 3 sources, and we found that they have kind of they are comparable to Schwarzschild in several aspects. For instance, they have very large redshift as you approach the geometry. It's ultra compact in the sense that it's 1.5 the Schwarzschild radius, the minimal S2 size. It's neutral, etc. But there are big difference, which are the multiple moments, strong axis symmetry also, and you have magnetic dipoles that are not super small. But yeah, I mean, it's a very simple geometry, and you can try to decorate them. And
also some spin. The A was something.
There is no spin. It's neutral and non-spinning. Yeah.
All this game is static.
Yeah. There is no small spin.
I see.
I mean, but yeah, it opens several doors where we can just explore and construct more complicated geometries from there, where we can hope to have something even more Schwarzschild, in the sense that you can first get rid of the vacuum bubble in between, put some flux. You can also build several construction, not to be, but in M theory, where the source will not be the same kind of bubble. You can also use the full n-soliton solution of Enzymes and Nordstrom, not only 2 guys, but and make a chain of plus Q, minus Q, plus Q, minus Q. Also, you can construct a bound state of BPS and anti-BPS black hole with a 3rd charge, P, where here it's like big fat black holes, not microscopic D1, D5 black holes. And also, you can hope to use the known BPS resolution of black hole horizon by, for instance, this D1, D5 and anti-D1, anti-D5 on top of a vacuum bubble, and resolving using supertube, for instance, which are the supersymmetric microstate of this black hole. Here, I guess you can have analytic solution, and you can do the same with the bound state of D1, D5P and on this supersymmetric partner by doing superstrata resolution. And here, I guess you will need numerical tools. Okay, so I will, yeah, stability, I think it's too late. I mean, we derive some stability from just one bubble, so the main ingredient of our solution. For that, we essentially studied classical stability and quantum stability by reducing to 5 dimensions. So it's just a 5D Einstein-Maxwell theory. We derive a gravitational potential from that, and we found essentially that the solution we had different kind of solutions. Some are gravitational instanton, so some top of the heel solution, and some are metastable solution. And also we found some kind of interesting Hawking-Page transition from the black hole and in the same regime, same temperature, same charge to the bubble we are studying. So I think I'll go quickly. I mean, if you have more questions, we have the workshop and we can ask later about stability. So the outlook of this project is, of course, adding more degrees of freedom would be nice to build more generic non-supersymmetric solitons in supergravity. So we can hope to add, for instance, Gibbons-Hawking centers. Ultimately, the nice thing will be also spin and also Chern-Simons interaction, because it seems to be an ingredient to scale more towards the black hole size, the Chern-Simons interaction, and maybe also add more flux degrees of freedom. Then also next step will be to have some kind of application in holography, so make them not asymptotically flat, but asymptotically adherent. This is also, I think, coming in the next months. Then to not use known solutions to build solitons in supergravity, but also exploit the integrable structure of the equation we have by inverse scattering and like backloom transformation to really build new solutions and not use directly the solutions that have been built in 4'th. At the very end, it's not only about construction. We need to derive some observables, how they differ from the black hole we have in the real world and stuff like that. Like geodesics, quasi-normal modes would be interesting. And also some stability existence aspect, how they can be nucleated, for instance, in the early universe, or also at the late stage of matter collapse before forming a black hole. Is it possible that those kind of non-trivial bubble structures that can emerge first before forming an horizon? So I will stop there and thank you.
Shall we ask from the audience in the Zoom session?
There was a question, but I answered it.
Okay, wonderful.
You can unmute. Okay, can hear you.
I just want to ask, mine should be fairly quick. At the beginning, I asked you can put angular momentum in. You mentioned you could Wick rotate y1 into t and t into a y1, but can you get Kerr? So can you get microstates of Kerr that way?
I'm trying, but for technical reason, it's hard to still have a, because the thing is, for instance, here we have some kind of KKM charges, but having a spin parameter, it's hard to still have some kind of bolt geometry that are still spinning. I mean, I have some issue. I mean, I cannot really have smooth solutions that are rotating for the moment.
Okay.
I mean, it's more like technical. I just don't know how to proceed. But like the equation, you can still technically take care, put in there, and try to make smooth bubbles. Smooth bubble replacing an horizon, but it's just singular.
See if you got more stability if you made the Kerr near extremal and things like that.
Yeah, I don't know. I mean, the thing is, I don't have solution.
Question from the audience?
No, I had a question about your last slide about the thing in progress. So before that, for the more there. When you have the N soliton analyzed and Nordstrom. So there, you're thinking about doing multiple bubbles.
Yeah.
And putting brain, anti-brain
exactly.
between them.
Yeah.
I see, which is doable, right? I mean, by your
I mean, the thing is, because
is it technical?
This ansatz is disgusting. I mean, the full solution is not beautiful.
Sorry?
I mean,
it's not beautiful, sure, but is it a technical problem, or can you just solve the bubble equations where they are?
No, it's perfectly doable. Yeah.
Oh, okay.
It's just like I mean, I can show you, but I mean, the solution is not pretty. That's all. Like to write a paper with such. I mean, it's just not pretty. But it's perfectly doable, and you can smooth everything regular. And stuff.
And can you put these things? Can you put? I mean, before you had these solutions which had various bubbles, can you make one of these bubbles to have anti-brain charge, or you cannot? Because before, I mean, you're saying that before you had m equals m proportional to q for every bubble you had.
Yeah.
There's a sort of there's a mass, there's a charge contribution, and
before
there's always the same ratio. Can you get one of those guys to be negative?
No, the ratio is not absolute value. You cannot make them either all positive or they're all negative.
But this is a different system, though.
Yeah, here it's just you don't use this linear branch, and I mean that's why it's not given in terms of harmonic function. Everything is more complex, but you can perfectly tune the mass and the charge independently. While before, the mass and the charge of each object was given by the same quantity for all of them. So, but here it's just a very different kind of solution of those equations I gave at the beginning. It's a solution, but you can tune the mass and the charge independently, so you can take plus q, minus q, whatever. It's not also plus q, minus q. You can take plus q over 2, plus q over 2, minus q. I mean, you can do whatever.
I see. And in principle, you can do so. I mean, I'm just asking whether you can do a long scaling, a long throat, which has some D3 anti-D3 at the bottom. So just because people who do flux compactifications, they need anti-D3 to uplift the sitter, anti-D sitter.
The thing is, I don't know what will be the BPS limit of this kind of object.
No, it's not a question of BPS object. The question is, for example, if you have a lot of D3 charge on one end, then you have this bubble, which is not very important, and then you have one anti-D3. If you can do a limit like that.
Yeah, this you can do. This is even simpler than what I have here. But if you do a chain of that, it will be harder.
Okay.
Let's thank again Pierre.